Okay, so here we have an example where we're going to look at wind-driven waves. So wind-driven waves are typically driven or pushed onto shore by some prevailing wind direction. So in this case, we have our land in gray, our shoreline, which is delineated by this thicker white line, and we have some waves, so this part is the ocean, and we have some waves approaching this shoreline. Now, we also notice that there's this little rectangular feature here. And so to mitigate or lessen the energy of these waves as they approach our coastal communities, these cities will oftentimes build coastal armoring structures or something to sort of lessen the wave energy that's breaking on their shorelines. So these kind of structures, which are outlined by this rectangle, these are like a shore parallel structure. They're often called breakwaters. So I'm going to label it here as a breakwater. So breakwaters are often used to protect harbors, so where people have, their boats moored along the docks. Breakwaters are often used to kind of lessen that wave action and protect the boats that are anchored in a dock. Sometimes it's also used for a recreational beach so that you don't have, say, big waves crashing where people are trying to go swim.
Okay, so I think I understand it. As the waves are coming in, some of the energy gets dissipated by these concrete structures that are off the shore. And that changes some of the wave properties probably as those waves come in as well.
Right, so what we want to look at is, say we have some prevailing wind direction that's pushing the waves, like in this case, kind of in a due north direction. But we see here we have this small coastal armoring feature. And we want to see how this feature changes our wave patterns, our wave propagation patterns as they reach the shoreline.
Okay, so as these waves are propagating in, this breakwater structure is going to slow part of those waves down.
Right.
But in the other areas that don't have any of those breakwater structures, those are going to keep going like they were. So essentially what's going on is it's causing a lot of friction right in this area here that's slowing the wave down. But the other part of the wave is not being slowed down as much. And so you have these waves propagating towards the shore, and they start to look something like this.
Oh, they sort of bend inward?
Right, and they bend inward and they refract towards city B.
Okay, so the wave front, say over here, away from the breakwater, is continuing at its velocity or maybe slightly slower towards the beach. But these waves, the part of the wave front that is interacting with the breakwater is forced to slow down. Right. So this structure forces this part of the wave to slow down. This part of the wave doesn't really feel the effects of the breakwater. And so it continues towards the shore, but overall you start to see this kind of bent wave effect.
Yeah, and fundamentally this really comes from the friction, the bottom friction that these waves feel from this breakwater.
Okay, so let's talk about in terms of sediment transport. We know these waves are carrying some particulate, right, within the wave, and also they tend to pick up sand from the beach. So if we look at the influence of this breakwater over time, we should start to see a pattern where sand builds up something in a pattern something like this. So we'll start to see a lot of sand build up in front of City B and sort of behind this breakwater. All right, so City B, it kind of has this focusing of sand in front of it, and sand that normally would have been pushed onto City C is now being pushed away. Same thing with City A. Sand that would have been pushed towards City A, all that sand is now being pushed towards City B. So we typically see erosion around City A, City C, cities that don't have a breakwater, and a buildup of sand around a community that has installed a breakwater.